Ready? Okay. Hello. How is everyone? Great. Okay, awesome. I'm also very excited for this talk and more excited to introduce our colleague in CC, Katrina Bossert. So this is actually really exciting because this is an area I know almost nothing about. And I think it's one of the fantastic things about our department that we get to hear about all these diverse fields. And I've been incredibly impressed with Professor Bossert as I've gotten to know her work and her career. So I'll do a sort of brief introduction now and before I pass it over to her. So she's a space physicist and she studies the dynamics of Earth's near space region. And I think what we're going to hear about today and what I think is incredibly cool about her work is that she leverages a lot of remote sensing instrumentation and analysis techniques and observational science to lead to a better understanding of coupling mechanisms in the thermosphere ionosphere system from above and below. And we don't know a lot about this region is what I'm coming to learn. And instrumentation and better data is actually critical for building better models in theory. So the work that Professor Bossert is doing is actually critically important for building a better understanding of this region. It's really foundational. She earned her doctorate at the University of Colorado in Boulder in aerospace engineering in 2015. From 2016 to 2018, she was an atmospheric and geosciences NSF postdoctoral fellow at GATS in Boulder. I don't know what that's an acronym for. GATS, should I know?
What is it? Global Atmospheric Technologies and Sciences.
Awesome. Okay, cool. Thank you. I should have written that out. Now I'm curious. Okay. In 2018, she's a research associate at Northwest Research Associates, and she became a professor at University of Alaska Fairbanks in 2018. But I think we're all very happy that in 2020, she decided to move here from Alaska. And had to deal with a rather significant climate change in the process, but has been an absolutely stellar addition to our faculty. And since she's been here, she's been awarded a number of really impressive things. I'll just mention a couple of them. One of them is an NSF Career Award, which for people that don't know, that's a really prestigious award for a junior faculty member. And she was also awarded the Air Force Office of Scientific Research Young Investigator Award, which was the only one in space physics that year. So that's pretty cool. And she is a co-I of a Phase A dynamic mission, which is aiming to study dynamical neutral atmospheric ionosphere coupling. Sorry, these acronyms that NASA has are terrible for me, but it sounds like a really exciting mission. And we're thrilled to hear about your work today. So please join me in welcoming Professor Bossert.
Thank you. Welcome to Geospace. We're going to talk a little bit about that today. And I'm assuming that because this is kind of a newer research area in CC, I'm going to give probably the first half or so is going to be a little bit of background, very broad background as to what geospace is, what space weather is, and what space physics is. So we will start there. And the first one is regions of Earth's atmosphere. So the Earth's atmosphere is divided into several regions, largely based on stability and what's going on there. So troposphere is something that we're all familiar with. That's where all the weather takes place. And then we get into the stratosphere, very stable region, warm region. And from the stratosphere, we get into the mesosphere. Some people call the mesosphere the ignorosphere. So if you haven't heard of it before, I'm not surprised. That's where all the meteors ablate and start burning up. That's that layer right before what we call space. Of course, once we get into space, as we'll discuss, we are not necessarily out of Earth's atmosphere. And so that's what I want to talk about today. What is geospace? So what is the definition of space? Okay, because it's a very arbitrary term when we're talking about, okay, are we off of the planet, or where is outer space? Some of the astrophysicists in here might consider space to be maybe outside of the solar system, and even. But so we typically define space as where a satellite can orbit at least once, and that is defined by this thing called the Kármán line. About 100 kilometers in altitude, which is not actually very high above Earth's surface. But I do want to put it into perspective. Below this region, the atmosphere is too thick for satellites to orbit fast enough, at least once. They have to go super fast, and the atmosphere is getting thicker, so they will start to burn up at that point. But above this line, we can have satellite orbits. Something that I want to point out is, you know, some people have considered space to be in the stratosphere, and you know, the atmosphere is very low up there. And so, for instance, some of these high altitude balloon jumps that have been done in the stratosphere, but it essentially looks like you're in space because the atmosphere is very thin there too. I still call that the lower atmosphere, but you know, it's all relative. Atmospheric scientists, you know, might as well be space to them. So that picture right there in the bottom corner is taken about 39 kilometers in altitude. So geospace is this term that we use to define the region around Earth that's still influenced by Earth, but you're not necessarily on Earth. So you can be traveling by, you could be orbiting in a satellite, and that's that region of geospace. So that is part of that encompasses Earth's outer atmosphere. It also encompasses Earth's magnetosphere. So this region is quite large, as we'll get into. And satellites are typically orbiting in this region called geospace. So the densities are pretty low in that region, though not necessarily zero. And as you get further away, satellites can actually stay in orbit for many, many years without experiencing too much drag. So another misconception is that geospace is a vacuum. Like once you get out of Earth's atmosphere, it's suddenly gone. But the reality is that Earth's atmosphere actually extends quite far into space. And then after that atmosphere, where you're still experiencing particle interactions, and you would consider the sphere to be moving and influenced by Earth, we start to have the geocorona and exosphere as well. So at the top of the exosphere, at the very top of that plot right here, that's around 10,000 kilometers. I'm going to point out that we have a density of particles of about 10,000 particles per centimeter cubed. So there's still a significant number of particles. And as you'll see when we talk about the solar wind, that's a pretty high number. That's 10,000 kilometers away. That's even beyond low Earth orbit. But by comparison, right, at sea level, we have around 3 times 10 to the 19 particles per centimeter cubed. So huge, huge differences. But we cannot pretend that space is a vacuum, geospace is a vacuum, because it is not. And these particles still play a role in satellite orbits and interactions with the magnetosphere and interactions with the solar wind. I'm also going to point out that beyond the heliosphere, so outside of our solar system, outside of the solar wind influence, the density is about 0.002 particles per centimeter cubed. So, you know, this is still quite significant, but compared to way out there outside the heliosphere. And the heliosphere is being that region where the sun doesn't have, or the sun has an influence. Okay, so how far does Earth's atmosphere or evidence of Earth's atmosphere extend into space? I like this picture because this is actually taken by NASA astronauts on the Apollo 16 mission, and it is showing Earth's geocorona. And so hydrogen actually gets excited by the sun and emits. So this picture right here is showing just how far that extends. And so the outermost region of Earth's atmosphere is largely hydrogen, but you can also get some helium and protons and electrons as well. And so more recent experiments have shown that the geocorona of Earth actually even extends beyond the moon. So we have evidence of Earth and Earth's atmosphere, particles from Earth's atmosphere extending beyond the moon. And of course, every year we get a few particles that get lost, but just putting this into perspective, planets themselves have a very large influence on space around them. So what else is going on in geospace? Well, we also have the ionosphere, and you know, this is probably commonly heard about because the ionosphere is something that can disrupt communications, and it's pretty maximizes fairly close to Earth's surface. Is about 250 kilometers in altitude above Earth, and as we'll see with satellite orbits, the orbits can be much higher than the ionosphere. 250 kilometers is well within the low Earth orbit region. The ionosphere actually exists because of the sun ionizing Earth's atmosphere. So we see an increase in the ionosphere during the day, and then it tends to decrease at night as you get more recombination of these species. The difference in densities between the daytime and nighttime is about 10 times. We also see differences occurring when the sun is more active. So when the sun is emitting more UV radiation and more activity, you have a stronger, denser ionosphere as well. So this ionosphere is going to vary with solar cycle as well. The ionosphere can be perturbed by things like plasma bubbles and waves. We can also have solar flare events on the day side that cause the ionosphere to increase drastically due to this increase in really strong radiation associated with the solar flare. So you hear about radio blackouts and things like that. That's happening due to this ionosphere increase. But the ionosphere itself is fairly close to Earth. And I like this diagram. So the ionosphere is this region right here. It extends to about 1,000 kilometers. And then we start to call ions outside of this region associated with the magnetosphere. And how do we make that distinction? Well, closer to Earth, we're going to have more influences driven by collisions and gravity. And so you get more into atmospheric dynamics within the ionosphere and ion neutral coupling. However, as you get further away from Earth, those ions are going to be strongly influenced by the magnetosphere. And there are all sorts of really neat things that are happening there that I don't have time to get into today, but you know, there are things like the radiation belt and all sorts of excitations associated with Earth's magnetosphere and magnetotail. So that region extends very far outside of the Earth. So that's that magnetosphere region. And then outside of this region, in our solar system in general, we have the solar wind. So the solar wind is not something that just happens during coronal mass ejections and solar storms. The sun has these long magnetic field lines that are extending far into space, and along those, these particles drift out. And the particles, you know, are close to the sun's or corona and close to the sun, get very hot, and eventually they can get hot enough to start drifting away. And so we get this thing called the solar wind. The solar wind can increase or decrease depending on solar activity, but it's always typically there. So the sun or the Earth is always in the midst of the solar wind. And so that has a makeup of all sorts of different ions that are from the sun, largely protons and electrons, but you can also get some other ions as well. It moves away from the sun at about 250 to 700 kilometers per second, and it itself has an associated magnetic field. Okay, so this is where Earth's magnetosphere comes into play, and it gets a little bit exciting. So we've got this wind with some particles. They are highly energetic. They have a magnetic field themselves, and then the Earth itself has a magnetic field. So we'll talk a little bit about that. But first, I want to talk about solar events, because this has been in the news a lot recently. All right, we had that huge solar storm back in May. This was actually caused by a couple of different things. So what happens when you have an active region on the sun is you start to get all of these coronal loops, this extending area where the sun's magnetic field is getting a bit wonky, and eventually it erupts, it explodes, and it blasts material out into space. Now, oftentimes, what happens is you can get flares that are associated with this region as well. And I want to point out that flares can happen on their own, and coronal mass ejections can happen on their own. And in fact, coronal mass ejections, if they are not pointing in the right direction, sometimes we don't detect them. We don't know that they have been emitted until they hit Earth. So that happened in 2023, and there was a surprise aurora taking place over Arizona. Nobody knew about it until it hit Earth, because that coronal mass ejection was emitted. There was no flare associated with it. So the flare is completely due to electromagnetic radiation, usually in the X-ray, but also strong UV. And we don't know about the flare until it hits Earth a few minutes later. And as soon as it hits Earth, we get huge ionization in the atmosphere. We tend to measure flare strength by the X-ray flux that reaches Earth. And then we also get these coronal mass ejections, and if they're in the right direction, they can hit Earth a few days later, sometimes as soon as 18 hours. So we've got the coronal mass ejection coming, and then what happens, okay? So let's talk about this. Let's talk about geomagnetic storms a little bit. So as I mentioned, right, Earth's magnetic field, we have a magnetic field with Earth, but we are always being exposed to the solar wind, okay? And so now we got to think about this a little bit, okay? Aurora are taking place on the night side of Earth. We see them at night. Why are they not taking place during the day side? It's not the solar wind hitting Earth that's generating these aurora necessarily. It is Earth's magnetic field that is causing particles to be accelerated towards Earth. So during just general times, doesn't have to be a coronal mass ejection. We get this buildup of energy in what's called the magnetotail, and it snaps back and sends particles back towards Earth. This is why you can see aurora even if there's not a geomagnetic storm. You know, when the solar winds are stronger, you can see them almost every night. When they're weaker, maybe every 2 or 3 nights. But we get these particles that get accelerated towards Earth's atmosphere and travel along the magnetic field lines and end up in these polar regions. And that's that region where the particles are usually emitted is known as the auroral oval. So this is why we see aurora in the polar regions. Auroras and geomagnetic storms in general are quite interesting because all of these particles that are being shot towards Earth's atmosphere actually heat the thermosphere up. And so we get heating associated with these. We care about geomagnetic storms, not just because, oh, maybe there will be something that causes all the power to go out from a very rare event, but more importantly, the heating can change satellite orbits and knock satellites out of orbit in some cases when the drag becomes so great because you have that heating and density change. So from here, let's talk about some orbits in geospace. So there are 3 regions or so that we tend to think of when we talk about satellite orbits. Low Earth orbit is this region that is less than 2,000 kilometers. Satellites that are pretty close to Earth. This is the popular region. This is like where all the communications satellites are being put up. This is where the Starlink satellites are being put up. It's cheaper to send satellites there. This is the region that everybody wants to put a satellite into orbit in. They can be even as low as 160 kilometers. That's not as common. You usually see them in the range of 500 to 1,000 kilometers. They're not just used for communication. They're also great for imaging because they're closer. So this is the region that's going to be most impacted by space weather. However, I'm going to point out that there are some other specialized orbits. This region between, you know, that's slightly between that low Earth orbit and also very far. So geosynchronous orbit, that's called medium Earth orbit. So for instance, GPS satellites are in that medium Earth orbit region. And GPS satellite orbits at around 20,000 kilometers, so 10 times the low Earth orbit region. And then if you want to put a satellite in an orbit that is staying at the same place and rotating with Earth, that's called geosynchronous orbit. So for instance, the weather satellites, whenever you see all the clouds or you check the weather, that's usually from a GOES weather satellite. Those satellites are up at about 35,700 kilometers or so. So there is a very wide range. And there are different aspects that affect all of these satellites. For instance, if you're further away, the satellite may be more subject to, well, you don't want it to be orbiting within the radiation belts, but maybe also subject to solar proton events and high energetic particles that can damage the satellite. Whereas if you're lower in orbit, you're going to be more influenced by satellite drag, thermospheric heating, and space debris. Yes. So another problem, another reason why we want to study this environment is the ever increasing space debris and this problem. So we're increasing the use of satellites, and space debris is now becoming a huge problem. The majority of it is in low Earth orbit. So yes, debris will eventually deorbit, but it can stay up there for many, many years. And the problem is that it's not just one satellite. If you have like a little piece or a little tiny grain of sand size or a piece of paint chip off a satellite, things are traveling at such a high speed up there that if that hits another satellite in the right spot, it can take that satellite out electronically. It can completely take out a solar panel. So these tiny little grains of sand are a problem, and they're nearly impossible to track. So we're concerned about it. It's a growing problem. This is a nice picture of the increasing space debris every decade or so, and that only goes up to 2010. In 2020 alone, the ISS had to perform multiple maneuvers to avoid large space debris. So this is a very common thing. So we've got these two aspects. One, we want to be able to understand where our satellites are orbiting. And I know it's easy to say, well, why track satellites? You could just put a full propulsion system on the satellite. That's so expensive. A lot of satellites that are sent up there do not have, high-tech systems. A lot of them are sent up and they're set on an orbit path, and we expect them to eventually decay. So for instance, in the terms of the Starlink satellites, they're put up with the intent that they will eventually fall out of orbit after several years, but there's not all these high-tech mechanisms on board, and that's the majority of satellites. So we do want to be able to track them, so we want to understand how density is changing in the thermosphere and how that can affect satellite drag, but we also want to be able to monitor the larger pieces of space debris. So there are kind of these two issues here. We want to understand density variations from day to day. We have a general idea of how density varies, but it's so general that if you were to try and use one of the existing models to track where a satellite will be in the next 5 months, completely off. So it's a big problem. And the second aspect here is it's also very difficult to estimate the drag coefficient. So this space debris is a growing problem. So it's not necessarily an easy issue. We aren't going to solve all the problems by understanding all the variability in this region. But we do want to improve our understanding, improve models. And to do that, we have to understand this region better and make better measurements within this region. So when I talk about the weather in geospace, I think everyone's mind is like, oh yeah, giant storm. And I have some recent news article titles, superstorms and radio blackouts and a geomagnetic storm that caused SpaceX to lose 40 satellites. So these things are important. We do want to understand them, but it's also very important to understand what happens on a day-to-day basis, because essentially we are building, like what I like to say is this is space infrastructure research. We are increasing a presence in space we really do need to understand what the norm is. What is normal? How do things vary on a day-to-day basis, or even seasonally? So let's talk about that. What's going on at the edge of space? So how do we predict weather and variability in the near space environment? Well, I think that there are two huge factors to this. The first one is solar influences, the sun itself. So there are whole fields dedicated to understanding the sun, how the sun is changing, how to try and predict solar flares, changes in the solar wind. But then there's this other factor, and that is Earth itself, because Earth's weather actually influences the thermosphere as well. And that's what I'm going to focus on for the second half of this talk. And I have two examples here. Just this one right here. This is an example of a solar influence on the ionosphere. You get all of these waves that are being generated. These are called gravity waves, not gravitational waves. They're just buoyancy waves. And they're generated due to this Joule heating associated with the aurora. So that's an example of a solar influence. Here's an example of a terrestrial influence. In fact, when you get very strong thunderstorms, those thunderstorms can generate waves, and those waves can propagate all the way up into the ionosphere and thermosphere system. So, and I will also point out that we have a disconnect between the models. So we tend to do really great models, weather models lower down. We have some generalized models higher up, and those models will take things like inputs associated with solar cycle and aurora and geomagnetic storms, but they're not necessarily talking to the models lower down. And so they're not accounting for things like convection, waves that are generated from below, and terrestrial influences. So we have limited measurements, and if we do include things like gravity waves, they're often just parameterized or ignored in the thermospheric models. Okay, so I'm going to talk about gravity waves because they are something that has a huge influence on the thermosphere. And you are probably familiar with them. They are buoyancy waves. I am sure you've seen them. They are just like waves in the ocean. You have probably seen them. I see them all the time over Arizona. I saw them the other day. Even though it's rare that we have lots of clouds, our clouds are really thin. And so it's easy to see these tiny waves. Sometimes they're ducted or Lee waves or just gravity waves themselves, but you can see them in the clouds. Okay, so these also exist in the thermosphere. The thermosphere is a fluid. So why study them? Well, for one, they can perturb the ionosphere. They can disrupt communications. They perturb winds and densities as well. They break and they generate turbulence and instabilities in the lower thermosphere that can increase drag. And they also, when they break, they can change the background wind flow. They can change temperatures when they break. And so all of these things can contribute to disrupting the thermosphere region and changing satellite drag. So I like to compare space weather in this near space environment to studying a ship on the ocean, because we're interested in weather and how that affects transportation on the ground and how that can influence a ship traveling through the ocean. Well, similarly, we want to understand the low Earth orbit region for spacecraft. I mean, are there times of the year where things are more turbulent, where you get increases in winds or temperatures, changes in densities? So we are essentially studying the ocean at the edge of space. And how do we do that? Well, I put a bunch of plots up. It looks like there are tons of measurements, but we are fairly limited, and we have to be pretty creative in how we study this region. So one of the ways that we like to study the region is actually using the ionosphere itself. Something that I'm going to point out is the ionosphere. It makes up about 1% of the atmosphere up there. So it is not this all-encompassing entity. About 1% of the thermosphere is ionized in this region. So it's still a very high density driven by dynamics. But the ionosphere allows us to do fun things like use radar to scatter off of the ionosphere. And so this is, you can see this is the night side. This is where we're getting some aurora. And this is daytime. This is a 24-hour period. The ionosphere increases. And if you look closely, you can see some waves. We can also use ablating meteors that cause plasma trails and look at the winds. We use very high-powered lidars that look up into the stratosphere, mesosphere, and lower thermosphere. We can use the different air glow layers, which I'm going to talk more about. And then we can also use what's become very popular is to use phase delay associated with GPS receivers to map out where there are perturbations in the total electron content, which is a map here. And this is actually a wave that's generated over a thunderstorm. So, and also we have some radiometry as well. So there are a couple of tools, we can use it all together. There are limitations. For instance, you see this region right here where it's dark. That's a region that we really don't have a lot of measurements of at all. And that's that mission that Sarah mentioned at the beginning, trying to get measurements in this region right here. So we still have a lot of gaps in knowledge. So let's talk a little bit about airglow. So there are constantly chemical reactions taking place in Earth's atmosphere. And in fact, the red and the green that you see with aurora, they're always there. They're just accelerated when you get a whole bunch of particle precipitation and you get tons of red and tons of green. But in general, this is just something that is always occurring. This orange air glow is actually due to the sodium layer. So when meteors ablate in the mesopause region, they form this layer of atomic sodium. And then we also have UV air glow and infrared air glow that are not pictured. So this is a picture from the International Space Station. I really like it because you can see all of these different air glow layers. And if you saw some of those aurora pictures on the horizon when people were seeing them this far south, you could actually see that red aurora and then the green aurora further down. That's due to those different regions in the atmosphere where those chemical reactions are taking place. So we can use this air glow to study waves that propagate upward into the near space region. So this is an example that I like to show because it's an example of a mountain wave that was able to propagate all the way up to 87 kilometers in altitude. You have probably seen this thing called a lenticular cloud over the cap of a mountain. Or if you haven't, maybe next time you'll become aware, these things that look like UFOs over the mountaintops. What happens is we get wind that blows over a mountain and you get this cooling and condensation, so you start to get a cloud form. These are usually associated with what we call mountain waves. So we have this displaced air, you get this upward motion that's associated with this. So it displaces up, displaces the air above it. Usually you have a little bit of a wind, and so you start to get a wave-like pattern. So this is this particular event that is modeled. The mountain is down here. This is the mountain over New Zealand, and you can see this cold, hot associated with this mountain wave that's propagating upward. This is actually a flight path that went over the mountain, and this is the temperatures in the stratosphere from 20 to 60 kilometers, showing hot, cold associated with that mountain wave. So this is an example of how we can use this air glow to study these waves. And of course, the other air glow layers are a little bit higher. But I'm going to talk a little bit about this, what's called hydroxyl air glow, that's centered near 87 kilometers in altitude. So we have a hydroxyl air glow imager placed in Poker Flat, Alaska. This has been running for several years now. This is a little camera. It actually looks at infrared emissions. And of course, you do get light contamination from other things, but the brightest thing in Earth's sky is actually this hydroxyl air glow. the brightest thing from Earth's atmosphere. Okay, you can get other things like the moon and stars, but this hydroxyl air glow is very intense. It emits in the infrared, and you can see waves moving through. So we have this placed in the polar region, and you can get all sorts of different phenomena that are occurring up there. I'll show you a few of them. We went to set this imager up in 2021. This is my former postdoc Kamal, Sophie, and Jess Berkheimer, Sophie Phillips and Jess Berkheimer were helping to set this up. And then you get this all sky image going on, okay? And so if you look here, you can see these long ripples across the image, and these are actually waves. Now we can unwarp the image and put it in terms of kilometers and distances, and you can see some of these wave-like features and also some of the smaller scale features like instabilities. And we are entering our 4th year of data, and I will get into what we're doing with that data in a second. So I mentioned that this is hydroxyl air glow. What is causing this? Why is it in the infrared? So up in this region of the atmosphere, we actually have this thin layer. It's probably a full width half maximum, about 7 kilometers. It's centered near 86 or 87 kilometers. And the hydroxyl molecule itself has all of these different vibrational and rotational states. And you're always getting these chemical reactions that are occurring, and the product is an excited state of a hydroxyl, and then it can de-excite. So you get this emission. And in fact, you get several different emission lines. Our imager is looking at this portion. This over here is the visible spectrum, so we can't see the hydroxyl air glow, but we are certainly able to detect it in our camera. And then there are many more emissions that our camera isn't even seeing that go further into the infrared. So we're just seeing a lot of these lines, and this is what's happening when we see this. And if you think about it, since this is a very thin layer, if you have a wave moving through the layer, we're going to be able to detect that. So I'm going to take the next 2.5 minutes or so, show you a video from this imager with some annotations. This video is sped up. It's occurring over about 5 or 6 hours. These ripples are associated with instabilities. They're called Kelvin-Helmholtz instabilities. You may have heard of those. They occur in the lower atmosphere as well. right, so that's that video. So we have millions of images, millions. And the question is, how do we work with them? And so we have a citizen science project. We want to know if there are times of the seasons where there's more wave activity in the lower thermosphere. Are there more instabilities, more turbulence? And so we need to analyze all of these images. And there are, we can obviously try and do this with just brute force. There have been other studies where graduate students just go through and say, I see a wave, I don't see a wave, I see a wave, I don't see a wave. But instead of having just one person, which can be biased, we've had thousands of citizen scientists looking at these images. We've had over 50,000 classifications of videos. And so the question is, can these citizen scientists, help us address whether there are times of the year where there's a lot more wave activity, where there's a lot more instabilities. And we can also use these citizen science responses for our own analysis as well, because there are a lot of different things going on in the images. You get things like moon reflections and stars, and sometimes you just get a random increase in density. And so you can use the citizen science responses in conjunction with analysis to help guide our interpretation of the data. I'm going to recognize all of the students that have been involved with this project. Our newest student, Tyler, is going to be working specifically with the citizen science data output. Jess designed this amazing interface, and then Karina, Jesse, and Sophie have also been participating in the data analysis as well. So I'll also point out, we're doing several different things with the data. But if you want to participate in this, you can check out that link. If you just Google Zooniverse Gravity Wave Zoo, this will pop up. And Tyler will also have a booth at our CC Open House. But to wrap up, I'm just going to give a quick overview. We do other things too. What else do we study? If you've ever heard of the polar vortex, something that is not happening today outside. The polar vortex is making other places cold. So that displacement of the jet stream is actually causing a disruption of the polar vortex. That actually influences the weather in the thermosphere as well. So these are some plots from my former postdoc, Kamal, who found that disruptions in the polar vortex were related to increased activity in the thermosphere. And Sophie recently has found that gravity waves and the stratosphere and disturbances to the polar vortex in the stratosphere actually cause ionospheric disturbances in the thermosphere ionosphere region. We also like to study aurora. So I think everyone's familiar with the red and green aurora. There are hundreds of different emissions associated with the aurora. In fact, hydroxyl itself has aurora, as you saw in that image. Or in that movie. This is aurora associated with carbon dioxide. We also look for perturbations in air glow. This is a plasma bubble over South America. This is using the Earth's UV air glow associated with oxygen to see waves and perturbations in the low Earth orbit region. Jesse's also doing work with that same hydroxyl imager to look at really high resolution measurements and instabilities associated with that region. And before I end, I always like to talk about how the research here also can be related to other planets. And I think there should be a lot more of that happening. Not as much as as it should be, but we get aurora and waves on other planets as well. Even on planets that don't necessarily have a magnetic field. Venus has an induced magnetic field. Jupiter, of course, has tons of gravity waves, and Saturn and Jupiter both have some pretty amazing aurora. In fact, Jupiter makes aurora and X-ray. So with that, I'm just going to end it on that note with some awesome pictures. they are not all from the geomagnetic storm. We have had aurora at other times. There have been several instances just over the past 2 years of aurora being observed over Arizona. This is one of those instances from 2023. This is something over Alaska. Sorry, you probably won't see something like that here. And this is actually really cool. This is called Steve. It's a new type of aurora that was discovered a few years ago by citizen scientists. So citizen science is always great. And with that, questions?
So the hydroxyl emission that you get is also a big contaminant for infrared astronomy. They're from the ground. Terrible. Sometimes it's impossible to remove from our images. Can you tell us, like, are you finding some things that it correlates with? Allow one to predict a good night or a bad night?
It depends on where your observatory is. Yeah, so it definitely, you get a lot more activity during times of the year where you have really strong convection and a lot of waves being generated. You get a lot of activity associated with the polar vortex, and those waves can actually propagate southward or northward. And the polar vortex itself actually seems to be linked to an increase in airglow, hydroxyl airglow emissions, and it can increase it by twofold even. So, if you have a big disruption of the polar vortex, you may have a huge spike in your hydroxyl airglow.
Hello, thank you for the talk today. It was really like a lot of stuff. So I have a lot of questions, but I'm gonna make just one. I don't know if the name English is Sprite, but there is like some phenomena that happens when you have thunderstorms, like red lightning. They're really, really fast, and you have to catch them like with a camera that is really, really fast. And sometimes I used to catch that in my house when I used to have like long story short, I observe the sky at night during the all day long, and I catch that. And I never understand how that is associated to the thunderstorms, because I know they're associated to the mesosphere, but you say that is all those relations about like the ionosphere and the upper atmosphere and the lower atmosphere. I don't know if you can talk about that or explain if you have observed that in Fairbanks.
Okay, so good question. Yeah, the sprite is the correct term for that. So sprites are just this instantaneous thing that are happening, and I don't know if we've observed any in our airglow imager. Part of that is because if there are clouds nearby, it's really hard to take observations. I think the emission associated with sprites is associated with, I want to say nitrogen, but there may also be some oxygen causing the red. But yeah, I think so, a little bit outside of my research area.
So I have two questions. One, is there a point at which we would have enough space debris / satellites to themselves change space weather patterns?
Do you mean like
it seems like they get in the way if nothing else.
Like they get in the way,
or like reduce the amount of solar radiation that would hit Earth, or just like is there a point at which they themselves become an effect that you would have to look at rather than something that is receiving the effects you're trying to understand?
I mean, that's an interesting question. I think there would have to be a lot to change the solar effect. Though there is something, I think it's called the Kessler effect, where they just assume that there becomes so much space debris that it starts colliding, and there's the point of no return, and they're all just doomed. I don't know. I mean, when we talk about space debris, it's really wide open, and it's more of a probability issue of, when you consider you have things that are orbiting up there for many years, there's a high probability that it's going to collide with something. 1 million pieces of space debris sounds high, but it's like spread out so much that it's not like, it's probably getting in the way sometimes of observations, but not.
Okay, so it's not keeping you up at night compared to the other thing. The other quick question. So do you consider like a sodium ion a particle? Like what are the particles that are reaching all the way up to like you had like 10 to the third? That's
oh yeah. So that's I think the most common species that's reaching that outer exosphere, that outer region, is hydrogen, but you can get some other ions too. The ions that are in that region tend to just be doing stuff with the magnetic field lines or the radiation belts. So they tend to be more associated with that, whereas the other atoms up there, hydrogen, maybe some helium, but it's mostly the light stuff.
It's a really nice talk, Katrina. I thought it was interesting in your introduction when you mentioned that the coronal mass ejections and the flares are not really correlated with each other, because there's kind of a cottage industry of people studying the early solar system that want to understand nuclear effects, like radiation effects from the forming sun onto meteoritic materials. And they use like X-ray observations of young stars to scale and say, oh, we can scale this to this spectrum of energetic particles. Is that just not valid?
No, so there is a correlation. They are correlated, but they don't. You can have one without the other. They don't always have to occur together, which probably just adds a little bit of complexity or noise to that calculation, I'm guessing. But
and one
yes.
more quick question, sorry. What is the origin of the neutral hydrogen at the top? Is that just associated from molecules farther down in the atmosphere, or
from Earth's? Yeah. I think so. This is.
It's the most abundant species. I was just wondering where it came from.
yeah. It's from Earth. Like that's the hydrogen around Earth is associated with Earth and Earth's atmosphere.
Well, nice job, Katrina. So your poker flat, how spatially varying are the gravity waves? Are you in the dark?
Oh, that is a great question. Okay, so the imager itself, the total field of view, edge to edge, probably about 1,000 kilometers, but reasonable data because you lose resolution at the edges, probably a couple hundred kilometers by a couple hundred kilometers. So we're looking at a specific portion of the wave spectrum. You can look at these things called kiograms, like make stitched together images over the night and maybe see some of the larger scale waves that are a couple hundred to a couple thousand kilometers, but most of the waves you're seeing propagating through are, a couple hundred kilometers down to maybe 10 kilometers. So there is a bias towards a certain portion of the wave spectrum. There's a bias towards wavelengths that are long enough in these waves to cover the imager. But there are imagers that are placed throughout the US, say, that make a chain of images. And then I really don't like to just operate in the dark. So I oftentimes utilize other instruments, satellites that are passing over. The incoherent scatter radar that's up there, I like to use that. And then obviously I work with a lot of modelers. So yeah, it's just one big thing. Like everybody in the field kind of has to work together to make the big picture of what's going on Earth.
Thanks. So when you're looking at the hydroxyl waves from Alaska, how high or how thick is the material that we're looking at? I mean, when we saw the aurora come across, it looked like we were looking at sort of two different levels. How thick of a region are we imaging?
Yeah, so the hydroxyl layer itself, full width half max about seven kilometers or so. Of course, that can extend, it drops off really rapidly on the bottom side. You really don't get much emission below 80 kilometers in altitude. It has a longer tail, but pretty much by 95-ish kilometers, you're not really getting too much emission. The aurora may have been in effect looking like it was a different layer, but what was happening is it is largely just excitation of that hydroxyl, though there are some other species that have infrared auroral emissions. But yeah, that was just like the accelerated reaction due to the energetic particle precipitation.
Very nice talk. Thank you. It's really interesting to see the effect of weather at much lower altitudes propagating to higher altitudes. This is maybe a little out there, but I was curious if there's any chance that like seismic activity could, propagate it all to higher altitudes. I have no idea. Is there any chance of something like that?
I'm so glad you asked that question. I had to remove that slide because I was running over time. But yeah, yes. So we see evidence of tsunamis and seismic activity. Interestingly, when you have an earthquake, it generates the acoustic waves associated with it. People have been trying to see those in air glow, but that's been harder. There have been some evidence in the ionosphere, so you can see the acoustic waves, and then you get these other waves associated with that seismic activity as well, more gravity wave spectrum, and we see evidence of those too. So there have been a lot of studies on earthquakes and tsunamis and coupling and being able to observe those in the hydroxyl layer in the ionosphere.
Cool. Awesome.
Hi, this is more about like the citizen science project and looking through those millions of images. I'm curious if you tried like coding any like pattern recognition like package to look through those images.
Yeah. So there have been many attempts to do everything from machine learning to which machine learning has its issues as well, because everything must be just so you apply it to one particular image or setup, and then it expects everything else to be the same. And then there have been other studies that have tried to use Fourier transforms, which there's so much going on in the image. I mean, even some of those waves you would expect to say, oh, you take a Fourier transform and you'll see the wave, but there's actually a whole spectrum of waves. So gravity waves come in a wave packet. There are tons of them that are always there. And when you take a Fourier transform, it looks like a blobby mess. And sometimes you'll see a couple of the waves sticking out, but it's really hard. And that's something that people have struggled with. And so that's where I'm bringing in the citizen science. Like I said, a lot of previous studies have been done where a graduate student will just sit there and look at the videos on each night and say, are there waves? Which direction is it going? You have one person doing these studies. The goal with the citizen scientists was to have multiple people coming at that answer, but also to point out those days where things are not very clear and you get answers like, yes, there are waves, no, there are not waves. And 50% of people are saying yes and 50% of people are saying no. And so what do those images look like? So in the end, we'll have a huge database that could be used for something like machine learning or AI, but we can also use it for other things as well.
Thank you.
I think we're out of time, so let's thank Professor Boser again for a fantastic talk.